Okay, and I'll just scrub out the crap part at the start. And then hopefully this will be better. Stop. Okay. Alright. Okay. Cool. Okay, so we have had, I guess, 3 lectures so far. And today we're going to go through something a bit more practical, looking at some kind of signal processing techniques. And we're kind of getting towards spectral DCM. So by the end of it, we'll have a spectral DCM. Finally. Like I said, well, I've been doing this very slow on purpose. We wouldn't go through every part of the differential equation. We've done what a differential equation is. We've solved differential equation on the whiteboard numerically. We derived the binomial model. That was lecture 2, I think. Last lecture, we kind of went a little bit more heavy into why the binomial model works in terms of linearization, Taylor expansions, and then went through the hemodynamic observation model. So yeah, today we'll go through the next couple of stages of this. We'll go through the homework first before we get started, but I'll give you a preview. We're looking at things such as stochastic DCMs, what a convolution is, and then what a Fourier transform is, and then how to apply the cross-spectral DCM. So today's a bit more of a hacky sort of session. We're kind of going through this Evernote that I've got, which I'll share to everyone once we finish the lectures. So in 2 or 3 weeks' time, and then we'll be kind of going through the code. So hopefully we all have downloaded the code, the repositories, including my repository on my Git. I'll be posting a lot more code on here, so you can start using that, especially solutions for last week's problem. Yeah, and we're going to go through now, and we're actually going to simulate a complete hemodynamic model. We're going to simulate the bilinear model. There's some code there to do yourself. We take an arbitrary input of A and C, and also we'll have the stochastic DCM, or we can say fMRI. So from when you finish from this, you actually have a model you can use and play using real data, not just some sort of made-up thing like the mosquito and the frog dynamical system. Okay, so how many of you did the homework?
I did.
I failed.
Okay, yes. That's what you did.
You didn't even send me the homework.
Yeah, sorry for that. Stuart, that's my fault. What's happening with that email stuff? But
it's not my problem.
it's not your fault, that's right. So I can't get you in trouble. So basically what we did, we solved the flow equation for the hemodynamic response function. So let me just put this double up. Okay. So the first term is the rate of change of flow, and then the second equation, ds dt equals, I forgot what it was now. It was kappa s minus gamma f minus 1. I think the last part is plus CFT. Minus. Okay, cool. So this is the first part of the balloon model. So look at the response of the flow and the vascularity signal in response to the neuronal input, Z. Okay, so what we should have done, we should have got here is this one here. So I'm going to make it a bit larger on the left-hand side. This should be the response you kind of should have got. This is the input, and that's a response when you just have two very, very simple, very close together events. So the first one is the one at the first new response there. The second response is the one closely after, separated by a point of 1 second. So as you can see, if you have these two together, what you end up with is a flow response that just looks like one really, because it's so close together. Okay, so did you two get that? Something like this? Did you get that? What did you get?
Why am I?
Oh, that's quite close. What was your DT?
So my DT is this.
Yeah.
Is the pattern is exactly
The pattern's right, yeah, just the amplitude's a bit off. Okay, I'll go through that and I'll put the code up to see how it's different. It's quite similar, it's very similar.
It's very similar, I don't know what's the problem with mine.
But this one, you should have got something like that.
Yeah.
But we'll go through that together after class as well. So one thing you should get after, when you have two inputs that are further apart, that equals 4 equals 4. So when you have this, you have an input here, an input here. Yeah? That's this one here. The input flow response looks like this. You have the kind of the initial response there, and the other response kind of kicking in. You have this additive response there. And as you get further and further apart, you see the dynamics change completely. The flow response changes. Okay? That's what you kind of should have got. And I'll put this code up if it's available. And this kind of represents what you do get in my experiments. If you have two related responses that are quite close together, it doesn't just look like this. If they're very, very close, it looks like just one response. And if you get the timing right, you get this extra kind of bump in there. Okay, that's one part of the homework. The next part I will show you is when you vary kappa. So when you vary this term here. So as we know from the last thing we talked about, and also our mode differential equations, this hit, what does it mean? This kappa term here, this term here. Shout out.
Decay.
Decay, that's it. Perfect, yeah. So the larger this is, the quicker the decay is. Okay?
Yeah.
If you have a very small value, which means a state-dependent term of rate of change, it's negative. Okay, so it means the decay becomes, if this is small, yeah, the rate of decay is smaller and smaller. So as you have here, this is the original case, but when you have less decay, you have more of these oscillations coming in. Okay, and when you have your decay rate to be higher, you have less pronounced oscillations. This second bump gets, it's hard to see here, but it gets lower and lower. If you make it on its linear, it's quite high. You don't even see the second bump. Okay, that's something you get. So we have this code, you can look at it, you can play around with it, you should just get a handle of these things. And it's the same kind of system we did before with the frog and the mosquito system, where we had those parameters where we varied them. The last part of the homework is to just change this gamma function here, gamma parameter. Now, if you look at these equations here, this is the coupling parameter between the oscillatory signal, S, and the flow term. Because we have, so S is on that side and F on that side. It couples the rate of change of S to F, which is why we get oscillations here. Okay? Does that make sense here?
Yep.
Okay. And if you change that, you can change the frequency of oscillation. You have the same decay, because we haven't changed the decay term in this case, or we change this gamma. That changes, since you hear the oscillation. It is still a bit, I think digest this when you have the code and play around with it so you understand these terms. Because these terms are present in DCM. Okay, you have terms which change the oscillations and also change the decay rates. Okay, cool. Good, good, good. All right, so we've got that, got something. And one thing you can also see, I would say, if we go again to this one here, you see that we have different oscillations, right? Now this isn't just some kind of made up in the air, made up model. This model's blood flow change. So there's a study which was done a few years ago, which looked at the changes of the blood flow in a developing rat. And what you do see is that the oscillation does change. It goes from something quite oscillatory or quite damped to something less damped. And so those parameters can actually track. So this gamma and that kappa, they track physiological quantities in terms of the elasticity of the vessels. So therefore, if you measure this and you find a particular oscillation pattern, this will give you an insight into the underlying kind of vasculature. That's what this does. That's what this models. Okay. Cool. Let's now go to something else now. So one thing we did see in our model, right? So if we had in this system here, okay, Now this here I want to talk about this convolution step. This all goes towards what our final aim is, determining spectral DCM, Fourier transforms, all that kind of stuff. Now, who's heard of a convolution before? Heard of a convolution?
I've heard of it.
You've heard of it.
Yeah.
Have you been confused by it? Did you know what it is, Mana?
Yeah.
Are you confused by it
Yeah,
as
they're
well?
confused.
Okay, good. So this is good. A new technique we can learn. So what we have, okay, so if you consider a signal, right, we have let's consider that case again of the flow equations. Who is that T? This is T. All right. Now if we look at the response here, we get this term here. Right? Yep. If we then do two of them, like this one and this one, what we end up getting is the following. We get the following. We get a bump, and you get this extra secondary bump. Yeah, I showed you that before, just then. This is exactly what we get. Now, if instead, okay, I'm going to do this creative thing. I'm going to look at the response of this one, and look at the response of this one. So look at them here. That's that one there. That's that one there. They're almost, they're quite similar. These are the responses. What I've done, I've just added these two functions together, really stupidly, and you end up with this. And this looks almost like a simulation using this to this. And you see that? I mean, assume it looks a lot closer to that if it's business. Now, this is kind of a surprising thing if you think about it. I mean, we've had these really complicated equations. We've gone together, written this up. You can find very complicated things to do this. You put it all together and you simulate this type of thing. And what I've done now, I've just taken this one and I've added them together really stupidly. Now, this surprising thing happens because the system is linear. Okay? This is a property of linear systems. So if you have two of these signals together, they kind of add that in an additive sense. They look like this. They combine in the same way as if you just added them together. Okay? Now this is something, like very special with linear systems. Now what you can do, mathematically what it all comes down to is a convolution. Okay? So it's that property of adding these little bits together to have something in the end. Okay? So this is how it looks like mathematically. You have on the left hand side you have this term, that kind of circular X-Man sign there. That means convolution, so it's just a shortcut. So you take a signal, then you take a time delay and you do this operation. Okay? If you don't understand integrals and stuff, just understand it's like adding many different signals together. Okay? So why is that cool? I mean, this is something, why have I done this? Why is this at all useful? Okay? Well, first of all, has anyone used a convolution before in their work? I'm going to say you all kind of did at one point. It's all hidden.
I did, yeah. We did.
Yeah, you did. You do what you say. It's all hidden. Okay, so why is this awkward? Now, like I said before, if you have these two signals, you can add them together in this interesting way. Why it's interesting is that if the only thing you need to do to solve a linear system is just solve the response to a very short impulse. So this one here. It's a very short impulse. It peaks. I mean, mathematically you solve the problem of this, just a stick. Okay? It's also called a Dirac delta function, if you're interested in things like that. I think they're very exciting. So you do this, and you look at the response to an impulse. Okay? And this here, we can call, too cold? Okay, sorry. G and T. So this here is the response to a single impulse. Okay? So what you need, all you need is this. Okay? You need this, just solve it analytically, numerically, measure it. So you can take someone in a scanner, ping them with something, and you look at the impulse response. Then you use this, okay? And you do that trick. You pretend your signal is like this. like that, and then you add them all together. All right, you put it all together. This is talking very abstract sense. It's not actually adding them together, but it's something like that, and it equals something like this if you add them all together. Now that operation is given by what this is, convolution. And you can do this in MATLAB yourself. So
You pretend that your input is like that, yeah? And then...
essentially, yeah.
And this is your signal, the
Yeah,
thing that you
yeah. So let's look at that. I have an example here in MATLAB. So let's look here. So you can open up MATLAB as well, if you like. It becomes a course where it becomes more hacky, hackathon. Back when I was young, I didn't have these hackathons. I'm not that old, maybe I wasn't aware they were actually happening. But I like to say that anyway. So what you can do, you can get like just a function, Gaussian function here. So I'm going to get all this and copy it into MATLAB. Okay. You make it yourself. So I'll just show you the example, then you can copy it as well if you want. Okay, so I have time, that, Gaussian function there, and I have this function here. Okay, this is the Gaussian response. You can say, for instance, as well, that you do an experiment and you find that your impulse response is this. Okay? Let's assume the kinetic response function is this. Let's assume that the EG response is this to a ping. Okay? So our G. Now let me just put this in here while you guys are typing. Put this here. Okay? That's where that is there. Okay, so I'm now going to plot this here. So I discovered, went to a scan, discovered the impulse response looks something like a Gaussian. Oops. Okay. That's how old I am. I'm an old person with computers and things. Ah, man. Okay. Here we go. So I went to the scanner and I found that it looked like this. Okay? So I say any response to an impulse looks like that. And then I say, okay, I'm going to do a new experiment. And I know the impulse to that region, the input to that region is something really messy and noisy, it's this. Okay? Now, if you want to then predict what it looks like, what you do this trick, this convolution. You take your input, this one. You take your impulse response, G, that one, or it's that one there, really. And you convolve them together, okay? If I lost anyone, this sounds familiar, people doing stuff, okay? I do that together, all right? I then apply a convolution. In MATLAB, it's actually quite simple. It's this conv function. There's an extra flags there, but don't really worry about it. Let's look at generic terms. You have this input function, you have your your input, and then your impulse response. Okay?
Why your imaginary input is just like a mess there? Why you just take the real inputs, for example 10 inputs that you have in your experiment?
Oh yeah, I could do that, yeah. This is just an example.
Oh.
But you can do it. You can instead do something like this. I was lazy because typing rand n is fast. But you can definitely do that. This is something completely like made up. Okay, so put this stuff together, what you end up with, this is your prediction. Okay? So you might read this in papers as the following, and I'll put it to them in that context. They will say the following. They will say, we went and recorded the impulse response function. This is our HRF, for instance. We then have a stimulus design or a new response we measured. For example, in Logothetis paper, he actually measured electrophysical recall. They could measure ZT, measure the neural input. Okay? Then they said we convolved this with the impulse response function, and we get a predictor or a regressor. And this is the prediction how it should look like. And then you take this signal and correlate with every other voxel or every other region in your brain. And that's most of your imaging, really. That's like kind of the basic stuff, really.
Is that response to the all 10,000 events or just?
That's right. Yeah, it is.
Just,
Why does it look so smooth?
And
That's a
it's
good
just
question.
1,000, yeah.
It's because it's been truncated. Hold on, let me. It's the wrong way around. Sorry. Yeah. It's a good point. Oops. Yeah. Switch loadings, yeah. It's a good pickup. Yeah. It looks like this. But why is it more smooth? It's because we know, we measure this, that the impulse response makes it smooth. And this is what Bolt does as well. It actually smooths out your data because it's so slow. Another way you can think of this is filtering, right? We're just taking our data, we're filtering by function, and then our end result is a filtered version of that. That's another way to think of it conceptually. Because they often talk about the Bolt response as being a low pass filter. You might have heard that. This is what it means as well in that context. And you can also define all of this in frequency space, which we'll do today, which is what spectral DCM is.
Can you repeat that again with the low pass filter in relation to this?
Yeah, so you heard the term low pass filter. Yeah. So the reason is because this here has all this high frequency stuff is not present in our impulse response.
Okay.
Which means when the result from here, it takes like the bulk signal, okay? So here, for instance, a very sharp signal gets smeared out. That all you get is like an approximation that, you can think about it in that sense.
Yeah.
It's actually blurry. Where does this actually happen? It kind of happens in a blurred direction from here. So it has the general idea that there's something happening there. It's low spatial, low temporal frequency. That's what it means. Make a bit more sense?
Yeah.
Cool. Any more questions on this? I'm glad I think it's useful. People understand convolutions now, hopefully?
Yeah.
A bit more? And you can use this code as well. You can just give it a try, really. Just try out a bunch of stuff. Change this kernel, and you get different responses there. Cool. All right, good. So that's convolutions, which is all good. All right. So, what we want to do...
Kev,
Yeah?
that convolution example code isn't on the GitHub yet.
No, it isn't. No. I'll put that up all in the code. So everything today will be in the screen capture, and you can also use that. Okay, so let's go back to this here. Okay, so we've done that there. And there's some examples there you can look at with the flow response. This is essentially what we did here. You can also look at things like blurring images, okay? You can have a Gaussian image, a Gaussian blur. You might have seen this in Photoshop, in like any type of rendering program, Gaussian blur. That's what it is, it's a convolution. You take a Gaussian function, you convolve it, low pass filtering, you want to use it as well, and it makes a blurry version of the photo. That's another way of thinking of it. That's just convolution. Okay. Cool, so next part, all right. So we're going to get to the cross-spectral DCM. We are this lecture. I do it at it's 5 o'clock in the night, 5 o'clock in the afternoon. Hopefully not. Okay, so there's one particular thing I'll tell you all about. So we went through, we did the bilinear model for task-based DCM, task-based fMRI, and we did it with this bilinear model. And we kind of show how it all works, okay? And you can put all this in a nice framework. Now, what I've actually uploaded onto the GitHub is a general form of the bilinear model. So if I go into here, and if you edit, it is called The Mosquito and the Frog. Love story of 2008. Okay, so what we got here, remember before how we actually approximated the ODE? We did that thing where like TI minus, please stop me and say yes if you remember this. If you don't, I'm a little bit concerned. You remember this sort of system we had you know, we had. Remember this? Yeah, we did that kind of stuff. So I told you, I went all of it to this mathematically, to the brute force way, and do a for loop, all that kind of stuff. I'll tell you, MATLAB can make life easier because it has a solver for you. You can do this automatically. So in some ways you can say I made this for nothing, but you understood a bit of the different equations before deeply, hopefully. So I've coded it all up now, so it's much more easy to use. So I've just set up the time vector, U1, so the first input, and that input, remember, was the same problem we had, the increase in mosquitoes, and we added mosquitoes to the system. Okay? It's just a formalism how to add inputs to the code, initial conditions as well. Yeah? And the simulation time. So all this is exactly what you coded before in lecture 2. Okay. Next thing, I've added connection matrix A. Remember we had the bilinear model. This is A. We can formulate the frog problem to the bilinear model. Also have the C matrix. Yeah, it's all good so far. All right. So this is how you solve it. You can solve it in MATLAB using an ODE solver. And this one is called ODE 45 because it takes all your inputs and forms into the solving system. Okay, so what you have to do for MATLAB, you call up an ODE solver, then you call up the function to code the ODE into MATLAB language. Okay, so I'm just going to show you this just for clarity. Okay, so edit. And I suggest you all have a read of this. Okay, so what it is, it does exactly that whole DT thing we did before, okay? What do? You take all your inputs and then transform it so we just look at the rate of change at one particular time. Because I remember, just to get you all back into what we did like dy dt equals something. Remember that? Then we did y of t I plus 1 equals something. Yeah? So this thing here, translate that into this MATLAB language. Okay? You actually calculate in the end the dy dt. Here I call dz dt in the bilinear model. Okay? It's all coded in this way. And I think you should familiarize yourself with this. Okay? And then I think one homework question I have here is that we don't have the b term. So work out here what the b term is. How to put the b term in here. So I think it makes sense once you start using it and reading it, just to understand what the ODE solver actually is, what it does. Okay, that's what it does there. And then we can look at now the mosquito and the frog. Let's just run the code. So if you have the code in front of you, just literally run the mosquito and the frog, press enter, that's it. Done. That's it there. Sorry, the text looks quite weird in its resolution. But we had that mosquito input and we have this change in the frog population and change in the mosquito population. So just as we had before, it's exactly the same thing. Alright? Okay, this is the bilinear model, it's there. And I wanted to flag this up just to show you that you can use it. Now, so, this is all well and good, right? But as I said before, for resting state, okay, we got at this task-free state, we don't have any inputs. This system don't have any inputs going into a specific region, any known inputs. Yeah? So we don't have C of U. That makes sense? Should we have B of J? No. We don't have this. We don't have this. Have I lost anyone? Everyone remember what these things mean? Yeah? We only have dz of t equals A of z. Okay? Yep. So let's pretend that's it. Okay. Is this enough for a resting state? Who says yes?
For resting, it's not, isn't it?
Sorry?
For resting, it should be enough.
Should be enough. Anyone else?
You're just saying A, right?
just in A. Okay. So we had sort of yes. What is the problem with this? It's a trick. Not a really trick question. There's an answer to it. So let's go back. It's quite cool. To this one here. Okay. So this problem here, what we did, we solved this together, class, remember? We had no inputs. So this is the same system. So if you look at here, you can see here, this is the 8 matrix, which is minus 1, minus 1, 0.1, minus 0.5, and 0 and 1. Yeah? That makes sense? We have no inputs there. This is exactly the same model. Now what do? We then set initial conditions. We said the frog started a certain population, mosquito started a certain population. After a while, what do we get? Yes, 0. So if you want to solve resting state, we want to model it, we can't do this because everything decays to 0. Yeah? If you look at this equation, what makes it go to 0? That's right.
Out of the system.
Yeah, that's right, which is that term there, yeah? Minus 0.5. Remember, it's a state-determined equation, state-dependent equation. Okay, so remember, if you have a state-dependent equation, you have a state-dependent rate of change, and it's minus, it means decay. Same as the flow equation. So in general, if we have an A matrix, right? And what that corresponds to is the diagonal. The diagonal of the A matrix, if they're minus, you can have decay in that single node, in that region. Yeah? So these off-diagonal terms, they correspond to cross-coupling, and this gives you the decay. In a very general sort of generalization. So it's not enough. It's not enough. So what do you need? Okay, now, oh, I did it there. Why don't I go back? Okay, I'm so good. I'm so good. Okay, so what do we need? Okay, so one thing, is rest really rest in your fMRI? It's also a big question. It was an easy answer, I think. It's not really resting, right? We're in there, it's task-free. It shouldn't really be called resting, it should be called task-free fMRI, I think. Anyway, so you have no task, but we have things happening. You know, we're meditating, we're thinking, we're breathing, and we have regulation, all this kind of stuff. All right. So if you take a single node, so the way you can think of that is the following: we have no inputs, yeah. We have region 1, region 2, region 3. We have some A matrix, right? That's what we said already, which connects things. Connection. All this kind of stuff. Yeah? So we have this ongoing activity which we can't actually model. It's so complex. You have this stuff happening on the neural level. You have temperature causing fluctuations in firing rate, fluctuations in mirror potential which causes fluctuations in firing rate. So we can't actually model that explicitly. It's really, well, they call it high dimensional. Okay? And where we can approximate it, we can model it in a certain way. Instead of saying we have inputs going in, what we do instead is saying each region, right, has an ongoing activity. And it is, what is this?
Noisy.
Noisy, yes. Noise. So each region has some noise in there. So we want to model a system which has noise in there. And each region has a noise. So to go back to the equation, we can write that out in our simplistic other dialect, which is the matrices, in this term here. This here, what's that? You know what it's called? Is read up above. You might know the answer to this, hopefully, or you, or Stuart.
Name of the equation?
Yeah. What type of equation is this? We have the A matrix and some random term. Somewhere written there. It is called a stochastic differential equation. That's what this is. Yeah, maybe not. Yeah. A bit hardcore there. Sorry. It's a very special class of equations, okay? It's not just having inputs, we have actual just noisy inputs. And these are also not easy to solve. Okay, you need special solvers for this. You know, before we had that dt equals something, or yti equals something like that. You can't just add a random term. You have to do something special for that. You have to integrate it in a certain way. Okay? So this is a stochastic differential equation. So also stochastic DCM has stuff like this for resting state data. You have noisy input on every region, every node, and you have the response. Now I want to be very clear on here, okay? This doesn't mean we just add noise to the end signal. This is not what stochastic differential equations do. So what does this mean? So for example, we can think of this. There's different type of noise, okay? We can think of an input, yeah? We can think of an output. This is flow or H pole, whatever you call it, anything. And then you can think of, okay, well the measurement, the scan is noisy, there's large scale drifts, all this stuff, okay? And that's noise on top. And then if you do many experiments, that noise goes to zero, okay? That's noise, or measurement noise. This isn't what SDE is. It's something else. What it is saying that you have noise in your inputs. Or you have a signal, instead of this, you might have something like this. So operationally, what it means is like, we have almost like a convolution. We have the input, we have the response, the system response to all of these, okay? So this extra noise may cause the system to oscillate as well. We might have no oscillation and we have the stochastic input and we just cause the system to say, okay, I'm going to reach a certain point and start oscillating because the rate of change terms are changing. This is what a stochastic DCM does. The stochastic differential equation is.
So where do we get the characteristics of our noises?
This is a good question actually. So you have to have a prior knowledge of what your noise will be. So you can measure stuff like you measure like memory potentials. You can measure things such as like even noise within your vasculature. So you have to have an a priori kind of estimate of what the noise is. The noise can also be like people call like pink noise or colored noise, white noise. What that also means is that you have noise at different frequencies. So if you went and measured this and did a power spectrum, and you looked at frequency and then power, it's just white noise, it's flat. Okay? Different colors of noise like pink noise, brown noise, might be something like this, might be something like this. You're kind of, maybe not like that, that's more structured than anything. But you have a distribution of the noise.
Why do you call them blue noise, brown noise, or that color noise?
No idea. I don't know why they call these things. You can't trust mathematicians. You can trust physicists but not mathematicians. I'll say it on record. Yeah. So this is what stochastic differential equations are. Okay.
So why, if we know our noise, so if we know the features of our noise, why don't we just remove it from our bolt and then?
It's a very good question. Okay. So what you're saying is, at this level or this level?
At that level.
The bottom level.
Yeah.
So you can. So the idea is, if you have just measurement noise, you can either fit something to that to kind of get rid of the noise. You can filter your noise as well, because it will be high frequencies. Or you can also do many measurements. So if it's system noise that's random, if you do a lot of measurements, this will end up becoming smooth. That's how you can get rid of them. And you can also filter it, you're exactly right. Because this will be high frequency if you take that out. However, if it's a stochastic system, you won't just have this high frequency, you might even have, because you might even have like more oscillations like that. So what I'll do, so we'll go back to the bilinear model. You can also add this not just to resting state DCMs or resting state models, you can add it to the bilinear model. So you have here, bilinear model you will know and love. Know and love, maybe just know. You have your C matrix there, and you have that U term there. Yep. And then you can add noise at different steps. You can add noise between the connections of the inputs to the regions. You can also add noise just in general to the system, to each node. So these are all kind of generic, or this is the full DCM really, has all the terms in it. You have stochastic stuff, you have the bilinear stuff. Okay? So if you want to solve this, you need a solver. So you might have seen in the email sent to download a package. What I asked you to download was to download a package that solves stochastic DEs. So if you're going to go back into your code, there's something called the stochastic mosquito and frog. Okay? So what I've done there, I'll just show you that. It's the same thing as before, but I just had this stochastic solver here. And adding stochastic terms there. So this thing, just go through your own leisure. It's just all code. All you guys love coding, I know that. Love, or at least know coding, and coding stuff up. This gives you a way to code all this stuff together. Okay? So I mean, I won't go into how this solver works because it depends it's quite complicated. It requires, I think, a lot of high-level mathematics to understand these solvers properly. But just know you can solve it. Okay? So now, I'm going to run the stochastic. And there we are there. Oops. So it's not just noise like I said before. We had the same input. I have literally the same kind of exponential function with the Gaussian as an input. And I've added stochastic to each node, to the mosquito and the frog population. As you can see, it's not just noise like this on a scanner. We're causing the system to do funky stuff. It's doing an extra oscillation. Okay? It's also doing extra oscillations on this too. These are real effects that are happening. You're driving the system to be oscillating and doing additional things there. Okay? And you can run this yourself if you want to run this in a full system. We've got the code in the GitHub. And DCM does this as well, but my one's a bit too easy to digest, hopefully. Okay. So now we've gone through what a stochastic DCM is. We've gone through convolutions. Okay. Okay. So what you want to do is see how it works in a real system. So here I have this system I pulled out from Carl Friston's paper, where he talks about resting state fMRI and DCM for resting state fMRI. I have a conductivity matrix. I have no inputs. Yeah. All I have is intrinsic inputs. I have these positive values, these negative values. What you'll notice is there's no self-connections. What's done mostly in these types of studies is just have these self-connections be negative and set to a value and fit. Okay? So it is implied there are self-connections in there, or intrinsic state-dependent connections, these little loops, in all these nodes. Okay? So now, there's a code in the GitHub as well. All this is here. It's called RS fMRI. It's old, so you can start simulating real data here. Okay? I have the A matrix, which is a 6x6 matrix. I put all those connections in. I took from the paper in that figure, and I put into this big A matrix. So let's just see how it looks like though before I do anything. That's the wrong A. That there. Okay, color bar in. Oh yeah, these are the diagonal, they're all negative, which means decay. The ones off the diagonal, that means the cross-coupling between regions, which is what the diagram has. Yeah? Okay. So, if you look at that code, what do we have? I've included no C, but I made it to 0, just for completeness. Some simulation time, inputs, a stochastic amplitude. So of course, you've asked the question, how do you measure this noise? And also, what's the amplitude of this noise? How noisy is your inputs? It's a very good question. It's a question that gets fit in the DCM as well. You have prior knowledge, then you prove that by optimizing your DCM. So you're fitting this. Okay? And what I've done is I've used the STE solver, and then for each region I've applied the hemodynamic model, which is that one there. So a lot of code in here, okay? A lot of code you can use. You can actually use this yourself if you're in research. If you want to have a go simulating. And so like Christina, if you want to, for your presentation, you can like put your own connections in and use this code directly if you like. So we have stochastic inputs to each of these regions. We have specified A, which is the connectivity matrix. Okay. And if you run this, I think this looks nice, but it's just me. There we are here. Oops. Okay. What I'll do is I'll change the font size. 12. Just add all this together. This work. Okay, well that sucks for the time, but you gotta get it. I've got different regions on the left-hand side. Each row is a region. You have V1, you have V5, LOC, PVC, FEF, and PFC. On the left-hand side, you have all the regions, neural inputs, or neural dynamics. On the right-hand side, you have all the board responses. So you can use this code yourself. This solves a stochastic DE and then calculates a balloon model to predict the board response. So you can just run this and sort of edit the code as well if you want to do any extra things. Okay, so this is what we have here. And if you kind of look at you can do the following. You even do figure core. So I'm going to calculate the correlation. Bolt outputs. Yeah. So you can calculate some real kind of or numerical experiment. You have this correlation matrix, which you all know, right? You have different regions. You have the 6 regions on each side. We have a way to connect 2 regions together, correlation. Now, does this look familiar to everyone in terms of correlation matrices and stuff? Yeah, we all know this. Good. We should know this. You're in Alex's lab and part of that framework, which knows all this stuff quite well. All right. Cool. So that's something, okay? Now, how do we actually fit models to this? How do we fit parameters to all this stuff? I mean, you can see here, we have this correlation matrix, which you normally get out from data. There's no direction of this, because correlations are in this sense, symmetric. Because you're talking about two different signals, just saying how do these signals vary with each other. That's what a correlation is. Yeah? Then the other thing of DCM, which I've talked about before, is that you normally have an input, okay? And then you take the bold responses and then you try to fit the bold response to what you see in experiment. This works really, really well if you know what the input is and you have some idea what the output is. But of course, if I ran this again, so let me run this again, the same code again. And I'll put them side by side. Oops. You can't, if you went ahead and tried to fit a model to this stuff, if you look at each of these time series directly, it looks different, it looks really different. You have to say that's a different kind of experiment. So you can't just do the simple kind of thing where you look at you take the signal that you get, predicted minus observed, look at the R squared difference between the two and say, okay, it's a good fit. You can't do that here because it changes all the time. We have the stochastic system, we have oscillations but you can't really capture those oscillations using this typical fit you normally do. You need something else. You need something to represent your data. You can't use correlations, like I said, because it's not dynamic. It's just one point in time, and it's symmetry. You have no direction. What do you need? You need something else. So what you need, what was done in DCM for fMRI, is that you'd use the cross spectrum. So you take two of these signals together, like a connection between these two, and you find how they vary with different time lag. Okay? And what you do, you use the Fourier transform to make this more simple as well. So that's exactly what cross-spectral DCM is, and that's, you go to most courses, they'll just tell you this, and that's it. Look at the manual, it's quite simple. It's very quick to tell you what it actually means. But now hopefully we'll go through a bit more of this. I mean, we started a bit late, so if you don't mind waiting until like 20 past or something, if you want to leave early, you can. It's all recorded. Okay. So what you need is this power spectrum, this Fourier transform needed for this. So let's go to this thing here. Now, there's a very famous tool in analysis, the Fourier transform. Who's heard of the Fourier transform? Who's used the Fourier transform? Yeah? Do you understand it?
No,
Yes.
we have to use.
You have to use it, okay, all right. So what does it do? Okay, so the Fourier transform is used to make power spectrums or power spectra. So what it does, you do this operation, and I'll explain what it is. You take your signal, you multiply by this factor here, which encodes oscillations at a specific frequency. Okay, so you're saying at a specific frequency omega, it's a radial frequency, what is the weighting of the frequencies at that frequency to the in total signal? Okay, that's what a Fourier transform is. So if you had a signal which had fast oscillations, slow oscillations, the Fourier transform will pick that up because of this integration here. You might have seen this all in papers and stuff. That's exactly what it does. The Fourier transform is. It's a very special type of tool you can use, because if you have this thing here, okay, you can then calculate the power spectrum. So what you do, you take the Fourier transform in any sort of package, you multiply it by its complex conjugate. That just means swapping the sign between real and imaginary parts. If you don't understand what it means, don't worry about it. It equals to this. And there's a function in MATLAB called conj, which does this conjugate for you. So you can read about it later if you like. This is what you can do. You can calculate power spectrum. So you might have seen, like the famous stuff, I would say, power spectra are more used in EEG than they are in fMRI because of the time resolution. So you might, one typical thing is, say, in EEG, when you have resting EEG, EEG, you have alpha oscillations, right? So to do that, you do a power spectrum using this formalization, and you get peak at 10 hertz and 20 and 30 on stuff. So this uses this formalism. This is what a Fourier transform is. Okay, so let's. I want to do an example for you. So I sent out some of these notes as well in the email. We can put it online. So let's look at this. Okay, now I'm going to open up some code. Let's clear all. I haven't given you this code, so don't try to find it. This is what it is here. So I want to have, I'll show you here. T, okay, so I have a sine wave. Okay. Yeah. What I've done, I've made it have a particular frequency. So when you can calculate frequencies, you take two of these things and find a period, and the frequency is the inverse of the period. Yep. Yep. It's how to calculate frequency. So you have one specific frequency. So if I took the Fourier transform of this, what would you expect? Then look at the power spectrum. Yeah.
Power at one frequency.
Yeah. You agree? You look a bit lost?
Well, yes, maybe.
This maybe. Okay. Like I said, the Fourier transform, what it picks up frequencies. Like in alpha, if you have 10 hertz, you pick up a 10 hertz in your power spectrum. So this oscillation can be encoded in your power spectrum. Let's calculate it. I'll show you the code to do it here. So I've just calculated. So in MATLAB, in most packages, they use a fast Fourier transform. So I've just calculated a couple things. The frequency, and then using this thing called FFT. FFT is what you calculate in MATLAB to calculate the Fourier transform. And surprisingly, it uses a very sophisticated package called the FFTW, which is also known as the fastest Fourier transform in the West. I'm not kidding, that's what it's called. It's an official name. If you go to fftw.org, you'll see it says it plain as day. Okay, cool. You do this, it's all in the machine before you.
Okay, lucky.
Okay, so what you see here, this is the power spectrum. And as Linda said, you get just a peak. Because you only have one frequency in there.
Have real unit, the power, what's the...
That's a good question as well. So power has real units.
The watt is the watts, yeah. What's
Yeah.
the, it's watts.
Well, it depends on your normalization. You can have watts, you can have dB, and it depends on what you put in front.
Oh, so it can be different.
Yeah, well, energy density and power spectrum depends on how it's normalized. So be very careful if you're looking at power spectrum. Look at how it's defined and look at the specific name. Don't use another name unless you're sure. Let's be very careful actually. Because they have different conventions. But just be careful, I would say.
So it's a single peak because they were all evenly spaced.
Exactly, yeah, exactly right. If I added noise to this system, to this signal here, what I'd expect is this thing to broaden. Okay? Let's do it.
There's only one frequency present in the signal.
Exactly.
So when you change it from its time series to its power spectrum, you just have representation of one specific frequency.
Exactly right. So I will do times 0.1. Fourier transform EG. So if I added noise to it, even just a little bit of noise to here, right? Of course, noise has high frequency, and look, this is like wobbling around. Okay? So if you do that, you'll see now in the power spectrum, you now see these little blips. This peak also gets slightly wider as well. And that's capturing all that's captured in this, how this looks like. So width, how the height of this noise in there, it's all there present in the Fourier transform. Yeah? It's all good? Okay. Let's look back at this. Yeah, another property that you can, the Fourier transform has, so that's code I'll make available in the GitHub after this as well. You can play around with that. Another reason why I love Fourier transform, why Fourier transforms are amazing, is this property. I'm not going to derive it, this is a very fundamental property. That if you take the Fourier transform of that derivative, okay, this might look, you might be like, why the hell are you doing this? More maths, stop it. But I'm going to tell you why this is important and why it's important for spectral DCM. If you take the Fourier transform of this, don't ask how it happens. I can show you if you're really keen how this is derived. That equals I omega f of omega. Okay? It means the derivative now is an algebraic equation. It's a Fourier transform of f times I, which is the imaginary number, and the frequency. Yeah? This is just a relationship. Don't worry how it's derived. Now, if let's take this property. Okay? Now let's go back to our system here. Okay? So dy dt equals that. Dy dt equals minus 0.1x minus 0.1y and dx dt equals y. Let's apply this rule. Let's add the Fourier transform on the left-hand side and the right-hand side. And I'll also add, let's add the input, okay? How does this all transform to that one? That one goes, let's use this rule. It's I omega, I call it capital Y omega. Just using that plain and simple, equals minus 0.1 x of omega minus 0.5 times I omega minus I omega y of omega plus u of omega. And the next one here is just I omega x omega equals y. So why is this important? Still, I haven't shown you the big reveal yet. So what have we done here? We've taken a differential equation, okay? We've applied this rule. Fortunately, involve all sides. We now have an equation which has no derivatives anymore. All this is now is an algebraic equation, okay? It's algebra. All we have to do is just rearrange this. Why is this important still, you ask? I haven't got to the point yet. Just take it easy, alright? You can end up with this. I'm not going to show you this to take too long. We're both running out of time. You can say y of omega equals, I won't show what this t is. And this is just what you take, you go through the maths yourself. Now, does anyone know why this is cool? No. It's really cool. The reason is, if I wanted to simulate this, I can do two things. I can go through everything. You know, if I want to find the power spectrum, I can use the equation, go through all the stuff I did before in previous lectures, and simulate it directly, and calculate the Fourier transform in MATLAB, plot it, and get an end result. We can do that. That's fine. However, this trick, what it tells you the Fourier transform of y equals this algebraic function, which is like 1 plus omega divided by something like that, times the Fourier transform of your input.
So what was t?
So t, if I rearrange to make y the subject and get rid of x, I can do that. Okay? That's what it means. So I don't have to even solve anything in terms of differential equation like that. I can just solve this. Take the Fourier transform of this, times it by algebra, and you get out what the Fourier transform is, the power spectrum expected.
So I guess I'm sort of starting to understand how does the power spectrum preserve time or energy.
So it actually preserve or get rid of?
Well, I don't know what, like
Gets
what is,
rid of
it gets rid of it. So then how can you get it?
So it gets rid of it by like a fundamental theorem in calculus, and it changes, instead of time, looking at frequency.
Right.
It does it by it's a certain property, mathematical
Yeah.
property, that changes differential equation operators
Yeah.
into just algebraic functions.
Okay.
So it just does, it's hard without showing you the maths, but
Yeah.
I'll say you can change everything into just algebra.
Yeah.
Okay? And then you can just calculate the power spectrum now. Instead of going over everything, you just calculate this. Why is this awesome? Okay? Still, why is this awesome? This is awesome, alright?
Yeah, it's really is.
Because it's so much quicker.
It's quicker. So what's the alternative? What is the alternative? I can go back to here.
You don't have to simulate any time series doing this.
Exactly right. I can go back, I can put this in. This is this is like 6 nodes. I can put, if I put 100 nodes in here, just simulating it once will take me a long, long time, okay? I'm talking like maybe a few minutes, all right? What DCM does is try to optimize, tries to find the best parameters. So when you do DCM, you're actually redoing this simulation over and over and over and over, like, you know, maybe millions of times. I exaggerate, but many, many times to find the best model, okay? That's why this spectral DCM, that's why stochastic DCM can take you days, weeks. I mean, Ian just left, but he's had DCMs that run weeks, okay? What this says here, I can reformulate everything if I just care about the power spectrum in this equation. This takes milliseconds to calculate. If you know what it looks like, you can if you know what the matrix is, the way to calculate this takes seconds, or maybe milliseconds as well. So you can now calculate the power spectrum without doing any of that nonsense. And this is it. So this takes, to calculate entire DCM, to do optimization and everything like that, can take you seconds instead of weeks. Okay? This is why this is important. I might go through this again. I just showed an example next week, but this is what it does. So spectral DCM, what it does, it tries to find these power spectrums, okay, in particular the cross spectrum, and it does so using this algebraic formula. Because you can change your A matrix into this. You'll find out what that is. You can put it all together. This is a big step, I know. This is going very quickly at the end. So I'm going to go through it a bit more slower next week, and I'll show you and put into context and all that kind of stuff. So I think the take-home message is spectral DCM is needed because resting state you can't determine tasks, and you have these random signals. You just need to get an identity of the fluctuations, the frequencies. That's why you use a spectrum, okay? That's one thing, sort of DCM. The second thing is, it takes a long time to calculate this in stochastic setting. Long, long time. And if you use these tricks, there's a mathematical trick here, for Fourier transforms, you can calculate it very quickly. That's a take-home message. You can change all of these equations into something like this. It makes it take seconds. That's essentially spectral DCM in a nutshell. The last thing it does do spectral DCM, it calculates cross correlations. But I'll show you next week in an illustrative example instead. But that's what it does. We got to that point. The end was a bit crazy, but once you see this bit more and more, you'll be like, okay, that's what it does. And you can use this formalism for any type of differential equation. I've used this formalism in my PhD, used in physics all the time, in geology, astrophysics, all that kind of stuff. Uses this formalism, this Fourier transform trick.
Sorry, the T includes a region.
That's
region
right.
Matrix.
Yeah.
Okay. And something else it should be. It's the matrix and what else?
So it calculates the matrix, and here I've said U.
Our inputs.
Yeah, so inputs you can do for just normal spectral task DCM,
Yeah.
but in our inputs instead for cross-spectral rested DCM, we actually input the spectrum of the noise. Remember before how we said things are like, we said we have white noise, colored noise, okay? You put that into here.
Does it kind of make it easier to input the noise when it's in the spectral form, because you sort of understand the shape?
Exactly, yeah. Because it's very noisy, but this you can actually model it.
Yeah.
You can do this. And in DCM, you'll see there's a model for this, what it looks like. And what you do, you optimize your DCM, you actually model the slope of these. Or you could say things like it tails off like that, something.
And so then, okay, when you have y,
Yeah,
did you then just invert that transform to get the time series back?
you can, yeah, you can. Exactly right.
Because we've spoken, so far we've spoken exclusively about knowing the A matrix, but
Yeah,
the whole point of it is to sort of discover the A matrix, right?
exactly right, yeah.
So it's sort of, so in the background is SPM just essentially permuting through all these kinds of tens of thousands of A matrices,
Exactly
doing
right.
this, and then there's obviously some way of fitting,
Exactly.
finding the best fit, or
That's right.
and of course that's then the evidence or the free energy evidence or something.
So the way it does, it actually tries to, it just changes them over and over and over again, and it finds the best sort of fit to the data in the spectral space or in task space, the actual time series. And it does so by a specific search pattern, which we'll talk, I mean, when we do it, I'll show you very high level how it works. It's it's very computational, and I can just show you just in general how it works. And it's always evolving as well. That's what it does. It permutes it, and it has like when it has like a region where it's close, it tries to get closer and closer. It gets a track region. I remember before how we had, so good question on that. Remember we had this here, that one. Let's just say our signal is like somewhere between here. What it would do, it would actually change that like a parameter. It will change that parameter so it kind of fits more and more. We'll keep on changing it so then you get some fitting. Spectral DCM does the same thing. Instead of fitting time series, it fits like the spectrum and all that kind of stuff. It tries to get closer and closer and closer to the evidence that's given. The observation, sorry. Yeah. So that's I guess all that modeling in a nutshell. We've gone through what a differential equation is. We've gone through an input. We've gone through the bilinear model, approximation of why it works. We then did the stochastic DCM today, and resting state DCM, and the resting state stochastic DCM, and finally the Fourier transform formalism.
So we are not using stochastic DCM anymore.
So
Because we have this.
it depends. Yeah, you can use it as well if you want to. So what people tend to do is like they say that they can use a spectral DCM first, this formalism, to get somewhere close, and then stochastic DCM to get a bit more refined. Because the problem with this, there's a big problem with this, is that if your signal, we do a Fourier transform, if you don't have enough time points, your estimate of the power spectrum is really poor. This is the problem with. This is why spectral DCM isn't used all the time. It's because of that. It's very poor. And I think it's best to show by examples. There's a paper I'm showing like, so if you have like 50 time points, you can't do it. For EEG, it's not a problem because you have so many time points. You can estimate the power spectrum really, really well. If you look at DCM for EEG, it's used commonplace, spectral DCM.
But with resting state, it's typical to get only a couple hundred volumes.
Yeah, yeah. They say it's very good for 600.
Yeah.
You need multiband for that. But, yeah.
UCI is at 150.
Yeah. You can use for 150. I mean, Adil Razi is in the building, I think.
Yeah.
So we can ask him and just say what his experience is and how bad it is. There's a paper showing it's less accurate.
Yeah.
It's a business of accuracy. But then what you can do then is then possibly use like spectral DCM as stochastic DCM as well.
Okay.
If you use spectral DCM to kind of get you in the ballpark and then convert
Yeah.
to stochastic,
Yeah.
at what time, I mean, maybe it's hard to answer, but are you likely to see time savings on the stochastic side?
Yes. Yes. Yeah. Not for resting state though. You can do something else. But so there's a paper. So I might have shown you this paper. One of the papers I sent actually talks about that. They do spectral DCM first and then do stochastic to make
Well,
it
that's a
faster.
task, this one.
Yeah, yeah. So not for resting state. Yeah. So we'll go through a little bit more of this thing. I'll just show you more examples. We won't do much on the board. Let's see what else we have here. Yeah, and we'll talk a bit more about what the actual cross spectrum is in the cross spectrum DCM. So I hope you all have a good sort of feel about this. Like I said, this take a while to digest these last parts, I think. But I think once you start implementing it, we're going to go through together some code, become much more clear. Because one thing I did not want anyone to do to take over this course is just forget all this stuff and just click. So that's what you can do in DCM, just click, 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 click. But you get some understanding of the dynamics and what all these things mean. And then, yeah, you can kind of critique it and also just understand why changes in the A matrices mean things. Yeah. Cool. All right. Thanks all for that.
Thank you so much.
Next bit.
No worries.
It's like a question, like when
Yeah.
you're simulating data and in this script, there's like some inputs. Like how do